elements, and each element tells you the number of calls of a particular call. So find close was called 62 times, find first file A 12 times, and so on. We did this for we collected about, the vector was 1,200 plus dimensions, 1,200 plus dimensions. So each malware specimen had one of those. What we did then is we computed a similarity measure. What is there are many similarity measures. This is probably one of the most common ones. If you remember from high school geometry, what a cosine is, it's very easy to understand. If you have two vectors like this and they're perpendicular, if you project one onto the other, you can't really. I mean, because the similarity will be 0. The more similar they are, the more they'll project. One will project onto the other, and the higher the score will be. Similarity measure normalized between 0 and 1. So we fudged around a bit with the threshold, and we assigned things to a family if the similarity measure exceeded a certain threshold. These are our results. We collected 77 malware samples, ran them against 17 AV scanners, and then we looked at their classification, and we looked at our classification with our scheme. And with about a threshold of 0.8, that means if the similarity was about 0.8 when it came to this very simple, unordered, just number of occurrence API calls, was about 80%. So our sweet spot was about here. You can see where the discrepancies were for these, for Beagle and for Enor, MyDoom, and so on. We had a few false families. We had a few missed families. You know, as you increase the threshold, the missed families, of course, increase because you require more stringent proof. So again, it's a fuzzy factor. Statistics is a fuzzy business, right? The good thing is it makes you more tolerant towards slight perturbations. An interesting side effect, even though intuitively this should be so, but like Oscar Wilde once said, sometimes it's the duty of the intelligent person to state the obvious. It's pretty impervious towards packers. We probably don't use much API calls and so on. We could classify it pretty well, or it well, in essence, it was impervious, and maybe we'll look at this a little bit more. So this is the summary. This simple sequence of API calls was robust towards packers, 80% accuracy, without even putting it into anything more complicated than this very simple database where we cross-compared with this mathematical cosine similarity model. What can you do? Well, you can never be too rich or too thin, and you can never have enough samples, so we should get more malware samples to investigate this a bit more. Again, technique-specific exploits to attack the kind of classification scheme can be run. What we can also do is build a bit more intelligence into the actual modeling of the sequence called using a finite state automaton. And this I learned from Zanero's talk, which was about an hour before. This is how I can hot patch. I invite you to have a look at his classification scheme, which went actually according to a system called arguments, something I hadn't seen done before, so I'm very grateful that I went to that talk. If you want to see related work, you can look at Sekar's work. He actually built a finite state automaton. Strange enough, he stopped. He didn't. I mean, it was a very good approach, and then he just stopped. He didn't really run it on too many things. Rabek built kind of a whitelist and so on, and Rozanov, that's a master's thesis at the Polytechnic in New York, did this, but statically. So he went to the code, statically disassembled, figured out the API calls, and did a very neat finite state automaton result on this. The final approach, again, so we had fingerprinting on opcodes, we had fingerprinting on API calls, is on graph models. The key idea is here. Represent the program as a graph, figure out some metrics of this graph, and again, construct a fingerprint that can be used in a statistical manner. In order to do this, one has to know a little bit about representing programs as graphs. And here's the whirlwind tour. You all heard, and you all probably did it, a function called an IDA. You can have the control flow graph. So what we first have is a program dependence graph, which includes the data dependencies and the control flow dependencies. So it's an augmented, if you will, control flow graph. This neat little graph from CodeSurfer can serve as illustrative purpose. The green arrows tell you the data dependencies, and the blue arrows tell you the control dependencies. So so sum equals sum plus I is dependent on I here, and I equals I plus 1 is also dependent on I because it updates itself. So the green arrows are the data dependencies, the blue arrows are the control dependencies. The T stands for we take the branch if true. System dependence graph, you can view, if you want the one-liner for this, as an aggregate PDGs augmented with call functions. So now we have everything. We have control, we have data, and we have calls. Calls between these procedures. again, from CodeSurfer, and I invite you to, I'll have it in the reference, to go and look at their tutorial, 30 pages, and that's all you need to know for the beginning. It's like the 80-20 rule, you get in there. So here we have, again, the same graph. We have our main program, our PDG here, and we have it augmented here with the calls to add, as you can read it here in the code. The main point to get from this is that these programs can be represented as graphs. The statements here are nodes, and the control and data and call dependencies are the edges. The thought here is this: given that this is a graph, and given that there's a rich theoretical literature on analyzing such graphs, and I invite you to look in the reference, read Mark Newman's paper, 2003, 67 pages, and you'll be up to speed. Is that we can find some features of these graphs, and again construct some statistics, and then figure out whether we can use this for classification purposes. Again, this is the most intuitive of the ideas so far. I haven't actually done this yet because I haven't assembled all the tools I needed, but I'm giving you some food for thought. I'm heartened to see that this graph-based approach is not, I'm not the only one who's thinking along those lines. Flake did this last year. He did it this year again in the challenge for RE tools. Then I went to the very nice talk of those UCF students, Sidewinder, who actually used this for reachability analysis. You know, you have a vulnerability down there. You have some sort of entry points. How on earth are you going to get it? And they use a genetic algorithm. Very nice talk. I invite you to have a look at it. A primer on graphs. What do you have to know about graphs? In essence, two things. Well, three maybe. The nodes, the edges, and the edges and nodes can have, actually four things. The nodes can have weights, the edges can have directions. Well, so direction means it has an arrow. This framework is so powerful that very many phenomena in real life can be modeled as graphs. I took here a random sample. You've heard all of the Kevin Bacon game. Kevin Bacon game is nothing but a little graph exercise that you can give to undergraduates. You have also thesaurus. You have telephone networks, internet networks. If you've ever seen that huge graph, you know, it's in essence a network graph. To my surprise, chemistry networks can be done with this: food networks, predator-prey, sexual networks, dating networks, whatever you want. The graph paradigm is so simple and so powerful, it can be applied to all these different places. I'll give you a couple of examples what I mean by measures that you can put on graphs. One is centrality. Centrality means importance. If to take something home, centrality just means importance. Now, I'll give you three centralities. There are more. One is degree, and we see here. This is a star graph, and just here for illustrative purposes. The degree centrality says how many nodes are connected to me. So, you know, I count the immediate neighbors. So here we see, you know, everybody has a normalized, you know, 0.25, except for the one here on the outer edge has 0.17 because they only have like 2 neighbors, and everybody else has 3. Now, closeness. Closeness is how close am I from all other nodes. In the star graph, of course, the closest one is the one in the middle, right? It has the highest value because it's easiest to get to every node in there. And the ones with the lowest value in the star graph are the ones on the outer edges. And here, this one here is a bit increased, and this one here too, because the closer you get to the middle, the closer you are to all other nodes. Between the centrality, that's a very nice metric because it conforms intuitively to our notion of importance. Not just how many friends you have, but how important are you to everybody else around you. If you are the go-to guy in your organization, you have a high in between the centrality. It means how important am I for any 2 nodes. Again, the one in the middle is the most important in this star graph. Not in a graph in general, but in this star graph. Why? All these, if this guy is gone, none of these subgraphs can get to one another. We see the ones on the outer edges are 0. Why is that? Well, because they're not important for any communication. Any 2 nodes can communicate without going to the ones there. So they're between the importance is 0 when it comes to how many paths lead through me. Okay? Now, another measure is motifs. Motifs are subgraphs that are connected, that recur more than it would be normal just by chance. So it's in essence pattern in a graph. We have here a sample of a primitive sample graph, and we have a little motif example. Why motifs are important? Motifs are important because they can give you clues. They're like like fossils for archaeology. If you model processes with graphs and you find motifs that recur again and again, you can well, those were 2 tautologies in one. You find motifs. They tell you something about the dynamics that drive the network. They tell you something most likely about the generative processes. And they tell you something about if the phenomena that you're modeling is top-down engineered. They tell you something of design principles in them. I'll give you an example. This is a feed-forward loop. This feed-forward loop, very simple. You find this in electrical circuits. For those of you who are EEs, X influences Y, Y influences Z, and X also influences Z. You find this in all sorts of biology, in chemistry. You find this in ecology, engineering, and who knows? We may find this also in our in our research. If you're interested in this, I'll show you a few references at the end that you can read up on. It's a very hot topic, finding motifs and so on. Okay, so what I was saying is this. Represent programs as graphs and find these measures on them and do analysis. Why do I think this is fruitful? I think this is fruitful because in every other area that I've looked at, and they've done this like in 2 dozen or 20 different areas, but we haven't done it really in a systematic way when it comes to our area. So I think there are some fruitful results that wait there. Related work to this graph-based fingerprinting, look at Flake's BlackHat presentation in 2005. Mihai is here. He'll be happy to answer any any questions on this here. If you're really, a code monkey and very code inclined, read the stuff about interprocedural static slicing. It will give you new perspectives on program dependencies. Flake's talk here for new challenges is nice. And again, as I said, these UCF students who did Sidewinder is also a nice approach because they use the graph-based approach to find this. Okay, if you are interested in what I've been saying, and I realize it was a whirlwind tour, if you want to know more about statistical testing when it comes to this categorical stuff, I refer you to Huberman and Everett. You can get this through your interlibrary loan or Google for some papers, or go to Fravia's lecture on how to get any book for free on the web. For network graph measures, if you're interested in motifs, go to Alon's work. That's very nice. Mark Newman is a nice survey paper, and immodest as I am, you can go to my course on the science of networks if you want. It's a senior level undergraduate course on network and network analysis. System dependence graph, again, if you need the 1-hour introduction, go to the Grama website and read the KISS paper. I've come to the end, and I'm also, my powers that be have sent me here so I can find people who would like to collaborate with me so I can stick students on certain projects like that, talented undergraduate students. So if you have something that you think is pedagogically useful along these lines or even other lines, I'm open. We can do this. And like with the airlines, I know you have a choice in talks, so I thank you for coming to mine, and I'll be open to any questions.